Multiple kernel learning. It is possible to construct new kernels by combining simpler kernels. If k1 of xy and k2 of xy are valid kernels and c a constant, then k of xy can be defined as follows. Either k of xy equals to c times k1 of xy, or k of xy equals to k1 of xy plus k2 of xy, or k of xy can be defined as k1 of xy times k2 of xy. All of these definitions are also valid. Different kernels may also be using different subsets of X. We can therefore see combining kernels as another way to fuse information from different sources where each kernel measures similarity according to its domain. When we have input from two representations A and B, then Ka of XAYA plus Kb of XBYB equals to VA of XA to the transpose times VA of YA plus VB of XB to the transpose times VB of YB. That is, V of X to the transpose times V of Y, which is, by definition, K of XY. Where X equals to X1, XASB, such a vector, is a concatenation of the two representations. That is, taking a sum of two kernels is corresponding to doing a dot product in the concatenation feature vectors. One can generalize to a number of kernels that k of xy might be equals to the sigma of k of xy, where sigma is summing for all I starting from 1 to m, which, similar to taking an average of classifiers, section 17.4, this time averages over kernels and frees us from the need to choose one particular kernel. It is also possible to take a weighted sum and also learn the weights from data. K of xy equals to sigma of eta I times ka of xy, where sigma is summing for all I starting from kernel with a weighted sum. The single kernel objective function of equation 13.27 becomes LD equals to sigma of alpha to the t summing for OT minus 1 half times doubling summation summing for OT and summing for OS of the term alpha to the t times alpha to the s times r to the t times r to the s, then times the third inner loop of summation, summing of sigma of eta I times ki of x to the t x to the s, where sigma is taken among all possible I. Okay, so this LD, which we solve for both the support vector machine parameters alpha to the t and the kernel weights eta I. Then the combination of multiple kernels also appear in the discriminant. G of x equals to sigma of alpha to the t times r to the t summing for all t times sigma of eta I times ka of x to the t x summing for all I. After training, eta I will take values depending on how the corresponding kernel ka of x to the t x is useful in discriminating. It is also possible to localize by defining kernel weights as a parameterized function of the input x, rather like the gating function in mixture of experts, section 17.8. G of x equals to sigma of alpha to the t times r to the t summing for all t times sigma of eta I of x conditioning on theta I times ka of x to the t x summing for all I, and the gating parameters. Theta I are learned together with the support vector machine parameters, Golden and Elpiding in 2008. When we have information coming from multiple sources in different representations or modalities, for example, in speech recognition, where we may have both acoustic and a visual lip image, the usual approach is to feed them separately to different classifiers and then fuse the decisions. We will discuss methods for this in detail in chapter 17. Combining multiple kernels provides us with another way of integrating input from multiple sources where there is a single classifier that uses different kernels for inputs of different sources for which there are different notions of similarity. You can check the publications of Noble 2004. The localized version can then be an extension of this, where we can choose between sources and hence similarity measures depending on the input.